All right, today we're going to talk about something called the chain rule. So the chain rule is a differentiation rule that deals with composite functions. If y changes dy du times as fast as u, and u changes du dx times as fast as x, then y changes dy du times du dx times as fast as x. So with the chain rule, we go from being able to find the derivative of x squared plus 1 to being able to find the derivative of the square root of x squared plus 1. Notice there's a function inside. Without the chain rule, we could find the derivative of sine of x. With the chain rule, we can find the sine of 6x's derivative. So a few more examples with and without the chain rule. So what is the chain rule? The chain rule says if y equals f of u is a differentiable function of u, and u equals g of x is a differentiable function of x, then y equals f of g of x. This is a composite function, and it is differentiable. And dy dx, the derivative of y with respect to x, is equal to dy du times du dx. Or in a different notation, d dx of f of g of x equals f prime of g of x times g prime of x. In my words, the derivative of the outside, leave the inside, times the derivative of the inside. To do this, you have to be able to determine which function is composed into the other. So that's where we're going to start. We're going to decompose some functions. I need to figure out what functions inside and which functions outside. So for y equals 1 over x plus 1, the inside function would be this x plus 1. So we'll call that g of x. My f of x function is going to be what's left if I made that just an x. Will be 1 over x, so f of x is 1 over x. And that means that y is f of g of x. We figured out our inner and outer functions. For part B, sine of 2x, my outside function is the sine of something, so my outer function, f of x, is sine of x. My inner function, g of x, is what's inside, which is just 2x. So again, y equals f of g of x, the way I broke it down. You want to write this part down because you could have called those other things than f and g. For c, I have y equals the square root of 3x squared minus x plus 1. Well, my inner function looks like it'd be the stuff inside, so my outer function is just what's outside, the square root of x. Don't forget the x there. And my inner function, g of x, is that stuff inside, 3x squared minus x plus 1. So I rewrote my function as f of g of x. Then I have the tangent squared. And this one, the outer function is something squared, so x squared. And my inner function, g of x, is the tangent of x. So y, again, is f of g of x, the way I wrote it. So let's use the chain rule to find our derivative. So first thing we do is figure out what function is inside of the other. My inside function is x squared plus 1. My outer function is x cubed. So y is going to equal something cubed. I'll call it u. U just happens to be a standard letter that we use a lot in calculus. And u is going to equal that inner part, which is x squared plus 1. So to find the derivative of y, dy dx, we take the derivative of u, which is 3u squared, times the derivative of u, which is 2x. But we need to switch u back to x squared plus 1. So dy dx equals 3 times x squared plus 1 squared times 2x. We would likely clean this up just a little bit and make it dy dx equals 6x times x squared plus 1 squared. This brings us to something called the general power rule. The general power rule, if y equals u of x to the n power, where u is a differentiable function of x and n is a rational number, then the derivative of y with respect to x is equal to n times the function u of x to the n minus 1 power times the derivative of u, or equivalently, d dx of u to the n power is equal to n times u to the n minus 1 power times u prime. So let's try that. We need to look again for our inner and outer function. My inner function would be 3x minus 2x squared. My outer function is something cubed. So to get my derivative, f prime of x, I start by finding the derivative of the cube part. I bring down the 3, my stuff inside stays, and I subtract 1 from the power. So the inside here stays 3x minus 2x squared. Then I multiply by the derivative of the inside, which is 3 minus 4x. And then we simplify if at all possible. I would personally multiply the 3 and the 3 minus 4x together, making my derivative, f prime of x, equals 9 minus 12x times 3x minus 2x squared squared. So we've got some practice you might have to do, but we'll continue our video. We're going to find where the derivative equals 0 and where the derivative does not exist. So to find the derivative, well, to find where the derivative equals 0, we have to first find the derivative. My outer function here is a square root, but then we've actually got another outer function, which is a square. And what happens when you square root a square? They cancel each other out. But the issue there is that when I square root a square, I definitely get a positive number. But there could be a negative if I just cancel them out. So we need to treat this as separate functions. We need to deal with the square root of something and something squared. So we're going to have an outer function, a middle function, and an inner function of x squared minus 1. So we're going to treat this as a triple chain rule. So to do that, we start with the square root. To find the derivative of a square root, we make it 1/2 times the stuff inside to the negative 1/2 power times the derivative of the inside. So now I'm looking for the derivative of x squared minus 1 squared. Well, I bring down the 2, and I keep the x squared minus 1, and I subtract 1 from the power. Then I multiply by the derivative of the very inside, which is 2x. So we rewrite this. F prime of x equals, let's see, we're going to have 4x times x squared minus 1 over 2 times the square root of x squared minus 1 squared. All right, I want to know where it doesn't, or where it equals 0. So I set my numerator equal to 0. That'll give me x equals 0 and x equals positive or negative 1. I also want to find where this derivative doesn't exist. To find where the derivative doesn't exist, we set the denominator equal to 0. I divide over the 2. I square both sides. I square root both sides. And I get x equals positive or negative 1. So the derivative does not exist at x equals positive and negative 1. Which means up here in my original answer, the derivative isn't 0 there. The derivative is only 0 when x is 0. So you have to be careful that it didn't actually make the denominator 0 as well. So now we have negative 7 over 2t minus 3 squared. To do this one, we want to rewrite something in the denominator as a power. So I want to rewrite this as negative 7 times 2t minus 3 to the negative second power. It just makes my life easier if I can do it that way. So g prime of t equals, bring down my power, making it positive 14 times 2t minus 3 to the negative third power times the derivative of the inside is just 2. So I would rewrite this as g prime of t equals 14 times 2 makes 28, and drop my negative power to the denominator, 2t minus 3 to the positive third power, and there's my derivative. Some special things for simplifying derivatives. You might want to factor out a common factor. You definitely want to combine like terms, and you want to move negative exponents. You don't want negative exponents in your answer. So let's try this one. X squared times the square root of 1 minus x squared. This is one big square root. So to do this problem, we need to use the product rule. We have x squared times 1 minus x squared square rooted. I'm also going to rewrite this. I'm going to rewrite my square root as a 1/2 power. So product rule, remember we take the derivative of the first, which would be 2x, times the second unchanged, plus the first unchanged, times the derivative of the second. For the second piece, we need the chain rule. We take the 1/2 down up front, keep the inside the same, subtract 1 from the power, times the derivative of the inside, which would be negative 2x. And now we need to simplify. So I have 2x square root of 1 minus x squared minus, because of this negative here, 2 times 1/2 makes a 1, so I have x cubed over, because I have this negative exponent, I move it to the denominator, 1 minus x squared. You could leave it like that. This would be a totally acceptable answer. Or we could keep going and actually combine this into one fraction. To do that, we need this part to be over the square root of 1 minus x squared. So we multiply by the square root of 1 minus x squared, which makes it 2x times 1 minus x squared minus x cubed, all over the square root of 1 minus x squared. And distribute my 2x, I get 2x minus 2x cubed minus x cubed, all over the square root of 1 minus x squared. So I could rewrite my derivative as 2x minus 3x cubed, all over the square root of 1 minus x squared. Either of these answers is totally correct, just depending where you look, you might see it differently. Let's try example 4.8. F of x is x over the cube roots, and this cube roots should go over the whole thing, of x squared plus 4. So the first step here, I would rewrite this as x times x squared plus 4 to the negative 1/3 power. I just would rather use the quotient or the product rule along with the chain rule instead of the quotient rule. I'd rather not deal with a fraction if I don't have to. So to get my derivative, I take the derivative of the first piece, which is 1, times the second piece unchanged, plus the first piece unchanged, times the derivative of the second piece. So I bring down my negative 1/3. I subtract 1 from my power, which makes it negative 4/3, times the derivative of the inside, which is 2x. And now I just start simplifying. F prime of x equals 1 over a 1/3 power in the denominator, so cube root of x squared plus 4, minus, I will have 2x squared over 3 times the cube root of x squared plus 4 to the 4th power. All right, I could leave it like this, but this isn't likely how you find the answer. With this being to a 4/3 power, we actually need to multiply by an entire x squared plus 4. Because that is the 3/3 power, which makes it 3/3 plus 1/3, which is 4/3 power. So we're going to get x squared plus 4 minus 2x squared. Oop, I lied. We also need the 3 in here. So I need to multiply that whole thing by 3. All over 3 I'm going to rewrite this as a rational exponent, x squared plus 4 to the 4/3 power. Distribute my 3, I get 3x squared plus 12 minus 2x squared all over 3 times x squared plus 4 to the 4/3 power. And combine my last like terms, and my derivative is x squared plus 12 over 3 times x squared plus 4 to the 4/3 power. Again, this answer or this pink one before I got a common denominator would have been okay. All right, now I have a rational function inside of a square. So I have chain rule and quotient rule going on in that order. So to get my derivative, we'll call it y prime. I bring down my power, which is 2, times the inside unchanged, and subtract 1 from the power, so there we go, times the derivative of the inside. And for the derivative of the inside, we have to use the quotient rule. So the derivative of the top, which is 3, times the bottom unchanged, minus derivative of the bottom, which is 2x, times the top unchanged, all over the bottom squared. So let's combine our numerators and try to get this as simplified as we can. I would probably multiply that 2 into my first fraction here. So 6x minus 2 over x squared plus 3 times, let's see, we get 3x squared plus 9 minus 6x squared plus 2x all over x squared plus 3 squared. Combine my like terms again. I have negative 3x squared plus 2x plus 9 all over x squared plus 3 squared. Now, I multiply. 6x minus 2 times the numerator of the other fraction. I get negative 18x cubed plus 12x squared plus 54x plus 6x squared minus 4x minus 18. And multiply my denominators, making it x squared plus 3 cubed. My last step will be to combine my like terms in the numerator. I have negative 18x cubed plus 18x squared plus 50x minus 18 all over x squared plus 3 cubed. And there is my derivative. And finally, trig functions and the chain rule. The derivative of sine of u is the cosine of u times the derivative of u. That's the only change we're making here. All of our other derivatives, we just do the derivative of the inside multiplied on the end. So to find the derivative of sine of 2x, I say y prime equals the derivative of sine is cosine, keep the inside the same, times the derivative of the inside, which is 2. We would probably rewrite this as 2 cosine of 2x. For y equals cosine of x minus 1, we take y prime equals the derivative of cosine is negative sine of x minus 1 times the derivative of the inside. The derivative of x minus 1 is just 1. So really, y prime equals negative sine of x minus 1. And then if y equals, the tangent of 3x, to get our derivative, the derivative of tangent is secant squared, still of 3x, times the derivative of the inside, which is just 3. So we would rewrite this to be 3 times the secant squared of 3x. All right, some more trig functions, and just to be careful with how the parentheses fall. So y equals cosine of 3x squared. We need to take the derivative of cosine is negative sine of 3x squared times the derivative of the inside makes 6x. Rewrite it and we get negative 6x sine of 3x squared. For b, I have cosine of 3x squared. Cosine of 3 is just a number. It's a constant. So I don't really need to do the product rule or chain rule or anything. I just bring the 2 down. So y prime equals 2 times the cosine of 3 times x to the 2 minus 1 power, which is just x. y equals cosine of 3x squared. Well, to get y prime, we do derivative of the outside. Derivative of cosine is negative sine of the inside, unchanged, times the derivative of the inside. I bring down my 2 times the inside unchanged, times the derivative of the very inside. So we're triple chain ruling here, which is the 3. Simplify this a little bit. 2 times 3x times 3 is 18x. We got a negative in the front. Negative 18x sine of 3x squared. For part D, cosine squared of x. This means to take the derivative, we need to deal with the squared first. So we bring down the 2, leave the inside the same, and subtract 1 from the power, so that's really cosine to the first power, times the derivative of the inside, so the derivative of cosine is negative sine of x. So really our derivative here is negative 2 sine x cosine x. And finally for E, the derivative of the square root of cosine of x. Well, we will bring down the power, so 1/2 times this unchanged, but subtract 1 from the power, so it's cosine to the negative 1/2 power, times the derivative of the inside, which would be negative sine of x. So my derivative is negative sine of x over 2 square root of cosine of x. All right. For this next one, we look for the outer function. The very outer function will be this cube. So to get my derivative, I bring down the 3, keep the sine part the same, and subtract 1 from the power, which makes it a sine squared, times the derivative of the inner part. The next inner part is sine. The derivative of sine is cosine. Leave the very inside the same, times the derivative of the very inside is just 4. So f prime of t is 12 sine squared of 4t times cosine of 4t. Now let's find the tangent line to this function at the point pi comma 1, and then we'll also find all points in the interval 0 to 2 pi with horizontal tangents. So to find the tangent line, we need to start with the derivative. So I need the derivative of 2 sine of x plus cosine of 2x. So f prime of x equals 2 cosine of x plus derivative of cosine is negative sine of 2x times the derivative of the inside is 2. I just need to know where this is at pi. So f prime of pi equals 2 times the cosine of pi minus 2 times the sine of 2 pi. The cosine of pi is negative 1, so this is negative 2, minus 2 times the sine of 2 pi is 0. So my slope is negative 2. And then I say y minus y1 equals my slope times x minus x1. So y minus 1 equals negative 2x plus 2 pi. Add that 1 over, and my equation of the tangent line is negative 2x plus 2 pi plus 1. Now I want to know where there are any horizontal tangents on the interval 0 to 2 pi. So I want to know where the derivative equals 0. So I want to know where 0 equals 2 cosine of x minus 2 sine of 2x. Well, to do this one, we actually might want to use a trig identity, but we'll just logic it out. So if I add the 2 sine of 2x over and divide by 2, I get the sine of 2x equals the cosine of x. So I need to look everywhere from 0 to 2 pi where the cosine is the cosine of an angle is equal to the sine of twice that angle. So I look at my unit circle and I see that that happens at pi over 6. The cosine of pi over 6 is the same as the sine of pi over 3. It also happens at 5 pi over 6. The cosine of 5 pi over 6 is the same as the sine of 5 pi over 3. It's also true at pi over 2 and at 3 pi over 2. If I wanted to, I could also graph these two functions on my graphing calculator and see where they intersect and get the approximate decimal versions of these. All right, so you will do some practicing.